Good morning and welcome to this new course on acoustics. It's called the Fundamentals of Acoustics, and the word acoustics implies a branch of physics, which deals with the properties of sound. Okay. In the simplest form, if we let's say imagine air through which sound propagates, okay, and we hear each other's voices and signals and sounds of animals. If we just imagine this medium in front of us to be layers of air, vertical layers of air, okay, and these regions have a constant mass, and suppose I give it a disturbance over here. That means somebody says something or disturbs this medium through a speaker. Then this first layer gets disturbed and it moves. As a result, this region of constant mass is now occupying a smaller volume so that its density goes up. The density goes up. Now as the density goes up, the pressure goes up. Corresponding to the density, there is a pressure rise. So now these regions of air which were earlier in equilibrium, now there is an it has gone unstable in some sense. Okay. There is a disturbance, and pressure rise has happened. Okay. So this pressure rise will now disturb the next layer, and the next layer will move. But because there is inertia also involved, air has inertia however light it may be, okay, this pressure will disturb it so much that it overshoots a certain equilibrium position. As a result, the pressure that went up goes down again. And meanwhile, the compression that happened to the next layer, here the same thing happens. The density has gone up. As a result, the pressure here will go up and will disturb the next layer. Okay. So this pulse starts to propagate forward at a certain speed. Meanwhile here, as this pressure disturbed this layer and this layer overshoots a certain equilibrium position, the pressure goes down, and as a result the high pressure on this side and the low pressure on this side, that layer starts to move backward. Okay. And as it starts to move backward, it overshoots again a certain mean position and compresses this a little too much, so that again the pressure here rises. So now each layer starts to oscillate, and you can imagine many layers now in between. So each of this layer is experiencing this oscillation, and meanwhile the pressure pulse is moving, disturbing each layer as it moves ahead. Okay. That is how sound propagates. So both there is an issue of stiffness. Air medium has stiffness. Okay. When you try to pump your bicycle with the pump, you will understand air has stiffness and air has inertia, and both these are involved in supporting a wave, which is the sound wave. Now in this course, which is, let me say it right in the beginning, is a graduate level course meant for MS, MSc, MTech and PhD students. We are going to study this phenomenon of sound, okay, both using mathematics and understanding the physics. Okay. And how will the course run? I will begin with a lumped spring mass damper system, spring mass damper system, okay, present its transient and steady state solutions, and move to what is called mechanical impedance. Mechanical impedance. That will be the objective, to understand what is mechanical impedance. Okay. Then we will look at waves on a string, waves on a string like a musical string, waves through a rod, waves on a rod or a bar. Okay. These two systems have the same form as the acoustic wave equation in one dimension. Okay. And so I prefer to present these two because these can be seen. Okay. One of the subtleties of sound is that it cannot be seen, it is heard, and human beings are more visual than sensing by the ear. And so these two systems where you can see, waves on a string can be seen, waves in a rod can be, at least there it is better than sound. Okay. So they have the same form as the acoustic wave equation in one dimension. So we will derive the governing equations and look at the solutions in great detail, okay, before we move on to sound, and that way it helps. Then we will derive the acoustic wave equation in detail. Acoustic wave equation in great detail. And then we move to studying the 1D acoustic wave equation, which will be easier now that we have done these two systems. After this we move to 3D sound. Okay. And we will study the 3D sound in two portions. One is exterior sound, and then later interior sound fields. Exterior sound fields and interior sound fields. So when we begin the exterior sound field, we start with deriving what is called the free space Green function. Free space Green function. And then we move to the Kirchhoff-Helmholtz integral equation. Okay. Now from here, in order to study a few systems, we will take a look at the spherical coordinate, and using the spherical coordinate along with the Kirchhoff-Helmholtz integral equation, we will study a few systems such as the pulsating sphere, piston on a sphere, piston on a rigid sphere, point source on a sphere, scattering of a plane wave by a sphere, and then we will move to piston in a baffle, which is a good model for a speaker. And following this we will summarize the results and understand the physics of exterior radiation, physics of exterior sound fields. In a very general sense, we will try to understand the physics. Okay. Following this, we will go and look at the interior sound fields. Interior sound fields, for example, in a rectangular box. Okay. Or a rigid cylinder. Here we will come across modes, resonances, and modal summations, modal force decomposition, and so on. Following this, we will look at what is called a Sommerfeld radiation condition, and then we will go to some practical aspects of sound, decibels. Okay. What are decibels? What are the measures of sound? How to measure sound, measurement of sound. What are standard ways of measuring sound? Then octave and third octave bands, octave and 1/3 octave bands. And so on. Following this, we will study solutions using integral transforms, and we will spend a few lectures on green functions. And lastly, we will look at lumped acoustic systems, Continuous systems can be lumped as spring mass dampers, and within that we will study the Helmholtz resonator and the side branch resonator. This is more or less the direction of the course. There will be some extra material here and there. Okay. Now, as far as the books are concerned, the books I am going to refer to, okay, I will to a large extent refer to this book, which is called Fundamentals of Acoustics, written by 4 authors, Kinsler, Frey, Sanders, Koppen. I do not know their initials, but it is a famous book. Then I will have my own notes, and I will also take a significant portion from this book called Fourier Acoustics by Earl G. Williams. This is as far as the actual texts from which I will take the material. Okay. However, there are good books on acoustics which I will mention here. One, of course, is Foundations of Acoustics by E. Skudrzik. Then we have Physical Acoustics by David Blackstock. And we have Theoretical Acoustics by Morse and Ingard. Yeah, for now that is about it. So, these are extra textbooks or reference books for acoustics. Okay. So, that is the introduction. So, we will start the lectures from the next class on the spring mass damper system. Thank you.